you will know that there are a lot of arguments against calories. And so I really wanted to discuss what a calorie is, how we burn them, how we eat them, why they matter, and help you understand what really is going on as we lose body fat tissue. Now, a calorie, of course, in the audio sphere, I need to kind of describe everything out. You will often see the word calorie written with either a lowercase letter C or an uppercase letter C. Now we're going to talk first about the lowercase calorie. So calorie with a lowercase c. A calorie, in this sense, is the amount of energy that is required to raise the temperature of 1 gram or 1 cubic centimeter of water by 1 degree Celsius. Again, 1 calorie is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. That is a calorie with a little c. Now, food calories, so when you look on the back of a food label and it says a certain food has perhaps 100 calories, those food calories are actually calories with a capital, a big letter C. And that can also be written as a kilocalorie or a kcal. Those are both very common. And a food calorie is simply 1,000, meaning, as I described, a kilocalorie. It is 1,000 calories of a little c. So that would be the amount of energy required to raise the temperature of 1,000 grams of water by 1 degree Celsius. Now, as I described that, perhaps some of you guys have learned that before in a class you might have taken in high school or college. Those who are more active in the fitness and athlete sphere perhaps already know that. But I say that to help you understand that a calorie is a unit of energy. It's a unit of heat change, right? And that's all it is. It is a unit that we use to measure things. And in the argument against calories, you will often hear people say things like, oh, well, calories don't matter. Not all calories are created equal. Not all calories are the same. And this could technically be considered as true in a relative sense, but calories are just a measurement. They're just a measurement. They're not a molecule. They're not a substance that we consume. It's a measurement of energy. So, for example, 1 calorie is a unit in the same way that 1 inch on a ruler is a measurement, in the same way that 1 second on a clock is a measurement. And, you could say not all seconds on the clock are created equal, but of course they are, literally. It's just that, perhaps time flies, more fast than when you are hanging out with a good friend or your partner, and time goes by very slowly when you're waiting in a doctor's office or when you're having a long day at work. Of course, the seconds are the exact same, but then relative, they may feel a little different. And that's the same way with calories, 200 calories of Twinkies or candy often goes by very, very fast, whereas that same amount of calories of vegetables, of broccoli, takes a lot longer to eat and helps you feel a lot more full. The calories are the same, but they just kind of change your perception about how you feel about those calories. Now, to kind of expand on this idea of calories don't matter, they do. Calories definitely matter. Calories are kind of a measure of the chemical energy within the carbons of a certain food. And that is really what we can simplify it down to. Because again, like I said, I think a lot of people misunderstand calories to think that it is some sort of a molecule or substance that we can ingest and then literally burn in our bodies, because that is a term commonly used, is to burn calories. But that's not the case. It's a measure of energy. But what is a substance that we ingest and release is carbons, the amount of carbons in a particular food. So for example, hopefully we all remember this equation from perhaps even middle school. We've learned this, the equation for photosynthesis. When a plant uses sunlight energy to create its own food, it brings in 6 molecules of carbon dioxide and 6 molecules of water. And then with that sunlight energy is able to convert those molecules into 1 molecule of glucose as well as 6 molecules of oxygen. That's why plants are so beneficial, is because they take the carbon dioxide that builds up in our atmosphere and releases oxygen back to us, which is what we want for our fuel. Now, that equation for photosynthesis, of course, it's very simplified, but it is the exact reverse of cellular respiration, which is the process, the chemical process that we and all other animals use to extract energy from our food. So in our bodies, 1 molecule of glucose together with 6 molecules of oxygen will be converted into some energy for our body to use, as well as 6 molecules of carbon dioxide and 1 molecule of water. The energy stored within those carbon bonds are what constitute calories. And we can, in fact, measure the amount of calories burned and the amount of energy we're using by tracking the amount of carbon dioxide that we exhale. Now, some of you guys may be familiar with this as well, but in the air around us, in the atmosphere, it is primarily, I think, about 70% or 75%. Perhaps you might need to correct me on that, but it is somewhere in the 70% range of nitrogen gas. And then the air we breathe is 21% oxygen, and then it is a very, very small amount of other gases like argon gas and even a very, very small amount of carbon dioxide. Now, when we breathe in the atmospheric air around us, it is 21% oxygen, and when we exhale a breath, it is usually, depending on how long you held it in your lungs, but usually 17% oxygen. So the oxygen saturation of that air that you inhaled and then exhaled went down by 4%. This is actually something that I learned in EMT school. As you talk about CPR, if you were to give somebody mouth to mouth, it's a cool thing to understand that there's still 17% of that air you're exhaling into their lungs by giving mouth to mouth during CPR, which should be an adequate amount to partially oxygenate them. Sometimes we get this, bad idea that all of the air you exhale is carbon dioxide. It's not, but that 4% of oxygen that we lost is made up for in carbon dioxide. And that carbon dioxide that we exhale comes from the sources of energy from our food, from whether that is a carbohydrate, whether that is a fat that we ingested, whether that is a body fat molecule that we have lipolyzed and used for energy in our bodies. The carbons, after we have extracted the energy from those molecules, the carbons will be exhaled. Now, as I've described that, I want to go into a little more detail about how we measure calories. How do we measure the amount of calories burned? You may have heard, it's very common to see on food labels that 2,000 calories per day is used for general nutrition advice in the United States. I actually think for many people that's a little low. I would say probably the average energy expenditure in the United States is about probably 2,500, so 2,500 calories. But anyways, I think we're all familiar with the fact that we eat and we burn calories. Now, how do we know how many calories we burn? Like if I were to give somebody a diet plan for them to lose weight, how do I know how many calories they burn? And the answer can be described in a couple ways, but the first one is exactly as I was talking about, the amount of carbon dioxide we exhale. And when we're measuring that, it is called indirect calorimetry. And so we can measure that in two ways, both of which are very cool. The first one is called spirometry. Now, you might have seen, like in an exercise lab, there are certain masks that will go over somebody's mouth and nose, and it will be, supplied with pressurized air for them to breathe in, atmospheric air, but then it will extract the amount of air that we exhale, specifically, and measure the carbon dioxide of that air that we exhale. And that is called spirometry. And by doing that, we can very literally measure exactly the amount of carbon dioxide that they're exhaling. And this is very useful to use when somebody's performing a bout of exercise. So somebody could run on the treadmill while wearing this. Somebody could ride on a bike or a rowing machine while they do this. Somebody could even, sit in some sort of a resistance training weight machine while they do this. And we measure the amount of carbon dioxide that is exhaled, and then we can use that to see how many glucose molecules, how many fat molecules must have been broken down to produce that. Now, another form of indirect calorimetry that measures this same thing is actually very, very interesting to me. It's called doubly labeled water. So, of course, the chemical formula for water is H2O, meaning there are 2 molecules of hydrogen and 1 molecule of oxygen. Now, if you look at a periodic table, it says the atomic mass, or the molar mass of each element on the periodic table. And the molar mass of a hydrogen is 1 gram, and the molar mass of oxygen is 16 grams. Now, this specially doubly labeled water is a solution of water that contains 2 different isotopes of water. An isotope is simply, it's the same molecule. It has the same number of protons and electrons as the molecule, but a different number of neutrons, so it has a different molecular weight, a different molar mass. So it will contain half water that is H2O, where the hydrogens are, they each weigh 2 grams per mole rather than just 1. And then they also contain, the other half of the solution is water that has an isotope of oxygen that is 18 grams rather than 16 grams. So both of these waters are going to have a molar mass of 20 grams rather than 18 grams of the normal water. And then what we can do is actually measure the person's urine, because we have the special isotope of hydrogen and the special isotope of oxygen. Now, as we burn calories, that hydrogen that is specially labeled will only be released in the urine. Again, when we burn energy, it is released into carbon dioxide and water, and that specially labeled hydrogen atom will only be released in the urine because there's no hydrogen in carbon dioxide. But then that specially labeled oxygen will be released both in the carbon dioxide we exhale and in the water that we release through our urine. So what you can do is you can collect somebody's urine and you can look at the differences in the concentration of the radio-labeled water and the oxygen, and use that to detect how much carbon dioxide was produced. Now, perhaps that was a little too much chemistry for some of you guys. If it was, I apologize. You might have been able to tell that I kind of stumbled over my words there myself. It is a very cool procedure, and it is incredibly accurate. It gives us a very, very good idea of how many calories somebody burns in a day. The issue with it, though, is that it is very expensive. It's very expensive to make the doubly labeled water, and it's very expensive to have access to the tools that we need to, test somebody's urine and find that difference in the specially labeled hydrogen and the specially labeled oxygen. It's very accurate, and it's very cool because you can give it to somebody and you don't need them to stay in your lab all day. And then you can still get very accurate counts of the amount of calories that person burned. The downside being that it is expensive. Now, there is also direct calorimetry. And direct calorimetry measures heat. And the calories we eat in food, of course, will translate to mechanical energy. The chemical potential energy of the food and the fat stores on our body they'll be broken down, and that energy will be released as kinetic mechanical energy in the form of motion, and then eventually all of that energy will be converted into heat, kinetic heat energy. And so there are special rooms, boxes that somebody can go inside of in, of course, some sort of a nutrition or exercise lab. And they're insulated and they're surrounded by this layer of water. And then the water will be measured for its increase in heat, and whatever heat increase occurred while that person was inside of that room, that will be considered our energy expenditure. Now, as I describe that to you, you probably have already noticed the limitation is that, well, these rooms really can't be very big. It's probably pretty hard and pretty expensive to make these boxes. But then also, they're not going to have windows. They're not probably going to be very comfortable and enjoyable to stay in for long periods of time. So if we want to see how many calories somebody burns in one day, but then we keep them in this little tiny box, we're probably not going to get a very good idea, because they're not going to have a normal day. They're not going to be walking around and talking to their friends or their spouse. They're not, it's probably not a very good way to measure like a daily energy expenditure. Same with the spirometry that I talked about. No one's going to keep that mask on their face all day. You have to eat, you have to drink water. So there's limitations to that. And so in that regard, a doubly labeled water is going to be the best way to accomplish that. However, direct calorimetry can be useful if we want to measure, again, like spirometry, the amount of calories that we burn during a bout of exercise, on a treadmill, on a bike, etc. Or I have heard of examples of people sleeping in a direct calorimetry room. And again, that might not be super comfortable, but it is supplied with oxygen for the people to breathe. It's not going to hurt them or harm them in any way. And it might be, more appealing for somebody to go inside of this room and then immediately just lay down in bed and go to sleep. That might be another implication of this direct calorimetry. Now, on top of that, the next thing I want to discuss is as we are burning calories, as we're releasing carbon dioxide, there's something that we can measure called our respiratory quotient. And it's something that I think is very, very cool. Basically, what we do is we measure the amount of oxygen that we inhale versus the amount of carbon dioxide that we exhale. Now, going back to that equation for photosynthesis, or in the reverse, cellular respiration, 6 carbon dioxides and 6 water molecules will be converted into 1 molecule of glucose and 6 oxygens. And so if you think about that for a moment, that means that if we were to burn exclusively glucose for fuel, which is how the body burns carbohydrates, all carbohydrates will be eventually converted into some form of glucose for cellular respiration and energy production. If we are using only carbohydrates for fuel, then for every 6 oxygens we inhale, we will exhale 6 carbon dioxides. So that is a 1-to-1 ratio. So our respiratory quotient will be 1. And if that's the case, if you measure that, again, through a mask, we will be able to understand that you are burning only carbohydrates for your fuel at that time. And that is usually done during very, very extreme levels of exercise, that your body is only burning carbohydrates. On the other end, if we were to only burn fats, we would have a respiratory quotient of 0.7. That means that for every 7 molecules of oxygen that we inhale, we would exhale 10 molecules of carbon dioxide. So if we had a respiratory quotient of 0.7, we would know that we were only burning fats. Now, of course, usually it's never on one end or the other. Usually it's going to be somewhere in the middle, and that just means that we are using a combination of each for our energy. Now, if we were to be only burning fats for fuel, usually that's accomplished during low intensity exercise, whether that is simply sitting around and burning calories, sitting or sleeping, or whether that is just going on a simple walk. That is why you'll actually hear many people recommend to just go on a walk for fat burning. Now, that is obviously, the idea is correct. When you're doing that low intensity exercise, you are burning primarily fat for fuel. However, it all just comes down to the amount of carbons coming in and the amount of carbons going out. So even if you do burn more or even exclusively carbohydrates during your exercise, eventually you're going to get to a point, you're not exercising all day. You will get to a point where if the calories you are eating are less than the calories you are burning, the energy needs to come from somewhere, and then it will be made up for in fat. Now, that's not anything against walking. I love walking. I think it is a great, great tool for everybody. Those who are seeking to lose body fat, I do suggest you employ walking. I do it myself. It doesn't really make you fatigued. It doesn't make you very hungry. Usually it can be very enjoyable. You can have a good conversation with a friend or with your partner, and it can be a very great tool for fat loss.